So welcome everyone. Thank you for joining today. Today we have the pleasure to have Hoshin Gupta as our speaker. He is the University of Arizona Regents professor, and he will be talking about KENS, Kolmogorov, Arnold networks. So thank you, Hoshin, and the floor is all yours.
Thanks, Leila. Arguably this presentation is a little bit rough and somewhat incomplete because as I dug deeper into this, I started getting more and more excited about it. I had read about it when it first came out in May, June. We discussed it at a meeting in Germany, actually Switzerland, over the summer when I was visiting Germany, and I got into it a little bit more. And more recently, I've been trying to understand how you fundamentally go from linear to nonlinear representations, and what are things like fundamental nonlinearities and so on and so forth, as a way of extending the language of information theory or machine learning, the way of building the language that we use to construct our models, which, as you know, is a big sort of topic focus for me. So this came along at just the right time, I think, to give me an interesting perspective. So these are the two gentlemen, Kolmogorov in the middle and Arnold on the right, both Russians, I believe, who are responsible for the theory that led to this. And as you'll see, that goes back to a paper written in 1956, which predates our modern universal approximation theorems for machine learning. So here's my initial comment, and we'll see at the end how many of you agree with me. But I really think it's worth a discussion. So I'm sort of convinced after my limited study of both MLPs, multi-layer perceptrons, and CANs, that CAN theory is going to be an important part of future machine learning. In particular, this paper that we're going to discuss was developed by Max Tegmark's group, a student in Max Tegmark's group, or colleague at MIT. And as you may know, Tegmark is a physicist and is very, very strongly interested in the idea of interpretable learning, machine learning, and using that for helping to do science, physics, and so on. So very consistent with my own interests. So here's my outline. We'll talk about the theory. We'll talk about the KN, Kolmogorov-Arnold network, so I'll just call it CAN for short, the architecture, and compare it to multi-layer perceptrons so you can see the similarities and differences. We'll talk about some issues of training and performance that they from the paper, taken out of the paper. Most of this taken out of the paper. Some comments about interpretability and its applicability to physical conceptual modeling, which for us means domain science. And when I say that, I mean in extension, in combination with other concepts such as spatial convolution filters or kernels, flexible or context-dependent attention or gating as used in transformer networks, autoencoders, other kinds of concepts. I think together with those, this whole thing could become a very powerful support for domain science. I'll try to reflect on what I think are the strengths, some potential directions for improvement, potential improvements that could be made, and then future directions. And in particular, I'd be very interested in collaborating with anybody if they want to pick up on these ideas and develop them in the context of their own research, because I think there's a lot of potential here. Okay, so you guys are all familiar with deep neural networks, the architecture where you basically have a number of nodes, and I'm going to use D, the notation D, to refer to the number of input variables that go into our model, into our representation. And then, you can have multiple hidden layers which process all that information. Basically, you can think of these as various encoding steps. And at some point, you might think of them as decoding steps. So the distinction is a little bit arbitrary. And then in any case, you can think of the last layer from the last hidden layer to the output as a decoding step. So the number of output nodes is C. So this is a multi-input, multi-output representation. And of course, the output could be a single value, but in general, could be multiple things. The paper we're talking about is Liu et al. Came out, as you can see, this is archived June 2024. They call it CAN, Kolmogorov Arnold Networks. A bunch of people there, and you can see Max Tegmark's name is on the end. Apparently, the first author is with the NSF Institute for Artificial Intelligence and Fundamental Interactions, but you can see colleagues from MIT, California Institute, and Northeastern University. And here's what they say in the abstract. They're inspired by the Kolmogorov-Arnold representation theorem, which we'll talk about. And based on that, they claim that CANs are promising alternatives to MLPs. They discuss, which I won't get into too much, theoretically and empirically, that CANs possess faster neural scaling laws than MLPs. Therefore, they approach learning and performance benchmark levels which are close to what one would predict by theory. They claim that CANs have no linear weights at all. I put a question mark on there because, as I'll show you later, that's not actually true. I don't think it's actually true. But what they're trying to emphasize is that in contrast to a multi-layer perceptron, where you have weights on the edges, those weights, weight parameters that you're going to learn, they're replaced by learnable univariate activation functions, which are and then they learn them by parameterizing them as splines. So we'll come back to that. Whereas in contrast, multi-layer perceptrons typically have the weights on the edges and the activation functions on the nodes. And this is sort of a reversal. It's sort of like you're putting the activation functions on the edges and you're doing a summation operation on the nodes. We'll look at that. So through various examples, they show results where they claim that CANs outperform multi-layer perceptrons in terms of accuracy, but especially in terms of interpretability. And they tend to, based on their results, they tend to emphasize their application to small-scale AI and learning science tasks as opposed to large-scale tasks. But of course, that remains to be seen as people discover better and better ways to train these things, initialize them, and so on. I tend to believe that we'll actually see larger scale applications. And then they emphasize, so they emphasize accuracy and they emphasize interpretability because you can actually intuitively visualize and interpret the models that come out of these architectures. And you can actually interact with them as humans. So you can put them in a sort of a human in the loop or a machine learning in the loop kind of scientific investigation process. And that's what they mean by this. They can be useful collaborators to help you discover mathematical and physical laws or modify them. So based on that, they're promising alternatives and they open opportunities. Okay. Here's the image from the paper, figure 1, and I'm going to redraw it to show it to you in a different way, but basically they're comparing the multi-layer perceptron on the left with the CAN on the right, and they show you the formula for a single layer network on the left and the right. I'll go into the details. And they show a network architecture on the left for the multi-layer perceptron and the right for the CAN, but as I'll show you, these are actually very, very similar or equivalent, but I'll redraw it. And then they talk about the fact that one of their main contributions is to extend the Kolmogorov-Arnold theory of the networks based on that, which have been studied before by other people, to multi-layer, so deep CANs, so to speak. which is not actually part of the original Kolmogorov-Arnold representation theorem. So as a result, they don't actually have proofs, but by extension, it's an area that people may choose to study in future, even mathematicians. Just to put this in context, so we're familiar with the fact that you've got the multi-layer MLP as a universal approximator theorem by Kurt Hornick, and that came out in 1989. But to just point out that in many ways, machine learning was actually inspired by the Kolmogorov-Arnold papers from 56 and 57. And you can find these online. And I'll talk about that in a little bit more detail. So we're going back all the way back to the early 50s as the basis for this. So of course, these various papers that have come out on multi-layer perceptrons as universal approximators, they've been proved for different kinds of basis functions. And so I can't remember what basis function Hornick used, but I know that it's been done for the rectified linear unit. I believe it's used for sigma functions in this paper. I'm not sure exactly. Whereas, okay. So here's their theorem. So what they say is given any continuous function phi is the mapping, where you're mapping from an d-dimensional input space, x, so xt is a d-dimensional input space, to a c-dimensional output space, r. So the mapping is z is equal to phi of x, okay? So z is c-dimensional and x is d-dimensional, where you define the inputs on the closed interval 0, 1. So that's easy enough. You basically just normalize your variables so that they fall in the unit cube. Then what they claim and prove with this paper is that phi can be implemented exactly or arbitrarily closely by a 3-layer neural network having d processing elements in the first layer, that's the number of inputs, 2d plus 1 processing elements in the next layer, and they're very precise about that. It's exactly 2d plus 1, and c processing elements in the output layer. So here's an example. You've got 2 nodes, so d is equal to 2. Hidden units will be 2 times 2 plus 1, so it'll be 5 hidden units, and then you're up to however many output units you need. Now this applies for d 2 or greater, doesn't apply for d equal to 1, okay? So that's important to keep in mind. So I didn't put it on the slide, but it's for d equal to 2 or greater, and that's because they're interested in learning these multivariate functional approximations. And the equation is the following. So you've got z on the right, it's a function of x, and you've got these different summations. So if I go to the inner summation, you're taking each individual input and you're learning and you're modifying it through a univariate function phi kj. And there are j of these because there are j inputs, okay? And as we'll see, you get k times j of them totally. So j is the number, j is the input, j is the index on input. So you've got d of these functions going from each input to each of these hidden layer nodes. And then you've got similarly 2d plus 1 functions going from from the next input to each of these nodes and so on and so forth. Okay. So this architecture is very precise. We can reduce this to 1, as we'll see in a minute, if you're just doing a regression, a basic regression. So what you do is you take every input variable, you do a nonlinear transformation on that unit variable, and they don't specify the form of these transformations. You do that independently on each input variable, and then you add them up together. And that becomes your output of your hidden node. And then you do that for every input variable for these 2d plus 1 nodes. So you learn essentially 2d plus 1 features, nonlinear transformations to learn 2d plus 1 features. And then you sum them up. And then you take that summation and you pass it through these these k nonlinear functions. So you've got nonlinear function univariate, then you do summation operation, and now you've got a bunch of new variables, and then you do the same thing again, and you sum them up. Okay. The theorem is non-constructive, doesn't give any indication how to construct the phi and phi functions. It only tells us that by theory, such a mapping must exist. And I'll be honest, I was digging into the paper. I can't exactly explain to you why, but it has to do with the fact that in any small piece of this cube, you can do a sort of something akin to a piecewise linear approximation. Anyway, it'd be interesting if somebody with a better math background than me could dig in and actually explain why this theorem is true.
Hoshin, just a quick question. Where does the index C appear in that equation?
C is the dimensionality of Z.
Right. So somewhere in that expression on the right-hand side.
So yes, I should have put, yeah, this should be for each of the components of Z. Yeah.
Okay.
Yeah, probably. So you have to think of phi as a vector mapping, not a scalar mapping. So I'm using this capital phi to represent vectors and using the lowercase phi to represent scalars. Yeah, but you're right. I probably didn't do that completely correctly. I need to dig into it. Okay. So you get these 2D plus 1 outputs, features that come out of the hidden layer. And then each of those is independently then transformed through another of these phi functions. So you're right, there would be a subscript, let's call it L or something, or whatever, another subscript representing the C's. Yeah. Okay. It does, however, lead to the popular rule of thumb for sizing the hidden layer as 2D plus 1 nodes. So back in the early days when, before machine learning became popular in the 90s, when Colin and I were sort of exploring artificial neural networks, we were sort of taken by this fact. It sort of gave you an idea of how large a dimension you had to unpack into before you compressed it back down. So this rule of 2D plus 1, okay? As we'll see, that'll play an important role. So essentially, what did they do with this? What's the main contribution of this proof? They established that if phi is a multivariate continuous function on a bounded domain, then it can be written as a finite combination of univariate functions, okay? Continuous functions on single variables. You can ignore the interactions between the variables and the binary operation of addition. And then you do that compositionally layer by layer. In their case, they only did 2 layers, okay? Or 2 mappings from the input to the hidden and the hidden to the output. And so essentially, mathematicians, when they look at this, say that what they really showed was that there's only one true multivariate operation, and that's addition. Every other function can be written using univariate functions and sums. That's essentially the theoretical sort of meat of what comes out of this theorem. So you take each independent variable and you basically do a nonlinear transformation of it. And just to give you a little forerunner to how this seems to be interesting and important, is you can think of this in a very similar way to surrogate vector machines, where you're doing kernel function operations on variables, and effectively transforming them into a different space using, in that context, they talk about it as a kind of a like a projection into an infinite dimensional space. So it's almost like what you can think of it as something like an infinite polynomial expansion, but using a finite representation. And So that's called a kernel trick in support vector machines. Then they go on to say one might naively consider this great news for machine learning because learning a high-dimensional function boils down to learning a polynomial number of 1D functions. We'll see exactly how many those are. However, because this is only an existence proof, not a constructive proof, these 1D functions can, in principle, be non-smooth, fractal, or whatever, and may not be learnable in practice. They cite these papers. And they go on to comment that because of this pathological behavior, the KA representation theorem was sentenced to death in machine learning, regarded as theoretically sound but practically useless. And so what Liu and the group at MIT and other people have tried to do is resurrect this and say, well, yes, that might be true, but let's restrict ourselves to things that essentially, it's okay for them. Let's restrict ourselves to smooth functions. Okay, you don't have to be non-smooth, but perhaps somebody will extend this in future. Yes, Joseph.
So is this saying that you can model an XOR even with a just addition?
I don't know the exact answer to that, but my understanding is that to model an XOR, you had to go to a two-layer or a multi-layer perceptron, not a single hidden layer, and that was eventually solved that way. So maybe it has some relationship to that. Yeah. So, but no, I don't know the answer.
Thanks.
As you can look, you've got basically a sequence of two mappings, and if I'm not mistaken, XOR requires at least those two mappings. Maybe you could dig into it. That'd be great. Okay, so this is the architecture as shown in a paper where they've got two inputs, and you can think of it as a three-layer 2-5-1 architecture going from bottom to top. So you've got two input units. The number of hidden units, as I said, is 2D plus 1. So if you've got 2 here, that becomes 5 hidden layer nodes. But as you can see, you've actually got 10 connections, 2 times 5. And each of those connections needs a univariate nonlinear function on it that has to be learned. And then from the 5 hidden layer nodes, you can go, in this case, I boiled it down to 1, 2, 5, 1. You can then go take those 5 H1 to H5, which are now your new features, univariate features. And then you learn 5 univariate function mappings, transformations of those, and then you sum them up. So the only thing happening at these nodes is summation. There are no activation functions, okay, as you would normally put on a machine, on a multi-layer perceptron. The only thing you do is addition at the nodes. So you've got these 10 input hidden activation functions. That's d times 2d plus 1. And you're going to have, in this case, 5 hidden output activation functions, which is going to be c times 2d plus 1. So you can count up how many activation functions you have. And then, of course, however many parameters are necessary to learn all these activation functions. And that gives you an essence of the order of complexity of what you have to learn. Okay. So normally we think of a standard CAN architecture as looking like this. I'll draw the same 2-5-1 architecture. You've got a bunch of hidden units, and you've got an output unit. And notice now you've got D inputs now only, but now you've got N hidden units. It's not constrained by this number 2D plus 1. And you've got weights from the first input to each of these hidden units. And you've got weights from the second input to each of these hidden units. And then at every node, you do summation, and then you pass it through an activation function, right? So you can think of the activation function as being ReLUs or sigmoids or anything else of your choice. Could be sines and cosines, wavelet transforms, Gaussian radial basis function, whatever the heck you want. But that's normally thought of as happening at the node, and very commonly the activation functions are all exactly the same. The most common one being the radial basis function nowadays. And then you get your features, so you have these so-called learned features, and then you multiply them by weights, you add them together and potentially pass them through another activation function depending on what you want to do. So if you're doing regression, that might be just the identity. If you're doing bivariate classification, it could be a logistic curve, a sigmoid, or if you're doing multivariate classification, then it could be a softmax operation, whatever it is you want to do. And so you can write that equation as looking like that. And what I've done in the second box is I've just taken the subset of operations here and call that S, which is then passed through this activation function to give the feature H. And then you take those features and you do this, you do this linear affine transformation, you pass it through an activation function. Then you take those outputs of the features, you do another linear affine transformation, pass it through an activation function, and so on and so forth. Standard machine learning architecture. Learnable weights on the links, selected operations on the nodes. Let's look at it from a CAN perspective. Here's your two input nodes, D. Now the number of hidden units is maximum 2D plus 1, so it can be less. There's a clear relationship there. You've got your output unit, and now instead of weights, you've got these univariate functions that have to be learned on each of the links. And you don't have your activation functions at the hidden units, you just do addition. And then you take the features that come out of that, and again, you pass them through univariate activation functions, and you sum them up, and that's your output. And that's the corresponding equations for that. So you can see there is this, if you go back, you've got this sort of summation operation. So you've got this linear operation, and that linear operation is being replaced by these nonlinear operation. And so you don't have weights because they're sort of, you could pull out weights on these if you wanted to, but they're basically subsumed into these nonlinear functions. Okay. And those nonlinear functions can be compositional or any form that you like, essentially. So let's take, and then what they do is, in this paper, they say this hasn't been done before, but we can extend this idea and we can go to multi-layer CANs. So the same idea, you start with the input nodes, you do the transformations, you add them up, and now you can have this matrix of learnable functions in the hidden layers, and then you can do as many hidden layers as you want, and then you can go back and instead of the fully connected final layer, you have this kind of fully connected final layer where instead of constant weights, you've got these nonlinear functions that you learn on the edges, and then you sum them up, and that's the output. Okay. All right. So in other words, you can think of this as a process of compositional operations. If I take a 3-layer multi-layer perceptron and I re-envision it using the CAN architecture, this is what you get. There's your inputs. You can think of the links, the first set of links, as being basically the identity function multiplied by a weight, right? So instead of a nonlinear function, it's basically a linear identity function. Or sorry, not linear, but an identity function. And then you put the summation on the hidden units. And then you put activation functions on these output links. And typically, those are either rectified linear units or sigmoids or any other activation function of your choice. And usually, these are all the same. Just a moment, please.
Has anyone tried training a CAN yet?
I played with them a little bit. for streamflow prediction, either like independently or combining them with an encoder just to post-process it. My results were not, I would say, decisive. Like I got very good results for some of the catchments, but also I got some not very high performance for some other catchments. But also there are like different type of cans based on splines, although like it's mentioned that splines work better, but I'm not sure that would be the general case for hydrological data sets as well.
Have somebody checking my HVAC unit. Was there a question there or a point of discussion?
Yeah, we're just talking about experience actually training them.
Oh, yeah. Okay. I can make some comments about that too. Yeah.
Hoshi, can I ask a question?
Yes, please, Sina.
So one question I have is that there is no trace of like bias compared to MLPs in this cans. And my experience with like in general regression is that MLPs without the bias term usually do not outperform MLPs that have bias. Do you think that's important here, or?
So in principle, you can think of those biases as being integrated into these nonlinear functions. Okay.
Oh, okay.
And a fine transformation is it's not a linear operation. So you can think of that as being part of that. I've seen versions of the CAN equation where they actually have these bias terms in them. So whenever you think of a nonlinear function, don't think there's no bias. Yeah.
Thanks.
Okay, so in this case, like in the first layer here, I mean, one way is you add another one here, right, which is an input. The other way is that it's sort of an identity here. You have this thing plus sort of a bias term. I mean, there's different ways to integrate biases into this thing.
Yep.
All right. Okay. And so the difference being that these are pre-specified functions as opposed to learnable functions, except maybe for the parameters. So their function, their form is designed by provided by the designer and sort of being learned. And we'll come back to that later. And then you could say that in principle, I could have another operation over here where it's either the identity plus a bias term, there you go, Sina, or it could be a sigmoid term, or with biases included, or rectified linear units, or whatever you want on the end, depending on what kind of output you're looking for. Is it regression? Is it probability, or squashed onto a 0-1 domain, or is it you could put a softmax on there, or whatever it is, various kinds of things. So that's just because when I looked at this, I said, there's clearly a very strong analogy. And what is that analogy? And in principle, there's no reason you can't think of a regular MLP as looking like a CAN, but in some restricted sense. Okay. And then they go on to mention a bunch of previous work. So there's not the first work on this. As far as I know, that paper is still on archive, and I don't know if this has actually been published in a peer-reviewed journal yet. Some comments they make about contributions. Most previous work has stuck with original depth 2 or with 2D plus 1 representation. That means other attempts to work with CANs. Many did not have the chance to leverage modern techniques like backpropagation. I have seen things online where people have suggested that rather than using the standard backpropagation and what's the optimization technique everybody uses? downhill gradient.
Deepest descent,
Yeah,
stochastic gradient descent.
yeah, stochastic. But what's the name? It's named after somebody. It's a popular one.
Atom.
Yeah,
That's a pack. Yeah, that's a
right.
library.
Rather than Atom, people have suggested that there are other kinds of ways to train these networks. So I haven't dug into that, but I know when I was in Switzerland at the meeting, somebody was looking into that. And you can find videos online. What they claim is their general contribution is in generalizing the CAN representation to arbitrary widths and depths, revitalizing, contextualizing it, and then using a lot of extensive empirical experiments to highlight its potential for AI and science, and emphasizing its accuracy and interpretability. They do at the end of the paper mention that if you're looking to build very large, high-dimensional networks, maybe you wouldn't use a CAN. But I think, that's still something that's open for discussion and investigation because people have not really dug into these very deeply yet. And, it wasn't very long ago when people were not using very large machine learning networks, and all of a sudden with power and various advances, you're now training billions of parameters. So I think it's it's something that Levenberg markered. Yeah. Okay. So here's an example to illustrate on a very, very trivial and simple example how you might learn a function that is interpretable using a CAN. Okay, and I'll use this. So let's say you've got this 4-input function, which is sine of x1 squared plus x2 squared plus sine of x3 squared plus x4 squared, and then the whole thing is added together, and then you have an exponent. So a sort of a function you might see in mathematics or physics or something. And if you draw this is basically what you get. You've got the 4 inputs, and each of those inputs is passed through a nonlinear operation, in this case, the polynomial power operation, then the summation, then the first 2 are passed through a sine, the second 2 are also squared and passed through a sine, then you add them and exponent. So, any equation can be interpreted as a directed graph in this sense, where you've got only addition at the nodes, and you've got nonlinear operations on the links. Okay. Here's another one where you've got x being passed through a sine function, which in this case has a parameter pi, and you could even have an offset, so you could shift the phase of the thing. So basically, there would be potentially parameters inside this nonlinear operation that you would have to learn. Y is just squared. You add the 2 together, and then you pass it through an exponential function, and you add, and that's the answer. In this case, that plus is irrelevant because there's only one pathway. And one of the things they talk about doing, and I know Techmark's group is big on this, is taking the equations from Feynman's textbooks and lectures, generating data from these equations, and then seeing if you could learn these functions. And some of you may remember we looked at a previous paper by Tegmark's group where they designed this thing called AI Feynman, which was a neural network whose goal was to be able to take data from all of these functions and to learn these symbolic representations. So that's a sort of a symbolic AI machine learning thing that they've done in the past. Here they're using the CAN architecture to do the same thing. And you can look at the paper and dig into the kind of results that they get there. Okay. So the whole point here is that you need to learn these one-dimensional functions rather than weights. Okay. And so let's focus in on one of these functions. Okay, so let's just take psi11 or psi1j, whatever. And one way to learn these functions that you could imagine doing would be to embed a standard machine learning artificial neural network, machine learning perceptron, as this function, and then learn that function, right? So you would take your input, you would multiply it by different pathways, weights. You would basically So in this case, univariate, so the plus is irrelevant. You pass it through an activation function, learn a feature of that thing, learn a bunch of features, and then do linear superposition, add them together again, maybe pass through another activation function, and that would be your psi. So in principle, you could imagine that, right? These could or may not be necessarily interpretable, right? Depends on how you design them. The authors propose instead to use B-splines. So what's a B-spline? A B-spline is basically, and it's really interesting to dig into, basically you've got this axis, which is the variable x, and then you have a bunch of basis functions. They look kind of like Gaussians. They're not Gaussians. There's a particular equation for the form of these. And basically, you take these basis functions, which occupy very specific locations along the 0 to 1 extent of your input variable, right, that you've defined. And you can use regular grids, irregular grids. There's lots of different ways to do this. Dig into spline theory. And then what you basically do is there are these control points which have values, parameters, which you learn. And what they do is they basically, B-splines function as piecewise cubic splines. You can do quadratic or cubic or any order splines that you want, so that they preserve continuity, order continuity, first order continuity of slope, second order continuity of the rate of change to whatever order you want. And then all you have to do is learn the parameters which basically superpose and add these things together in order to generate the output function. Okay. And in this case, they've chosen basis functions that are smooth. So of course, your output function is smooth. One interesting property of this that we'll come back to is that because the cubic splines are local, when you change the parameters associated with one of those cubic splines, it leaves the rest of the function, the approximation, alone. So you can change part of the function locally without messing with anything you've learned about the rest of the function in another portion of the data domain. Okay, so it has this very nice property of being able to learn a global function, but being able to adjust it locally without messing up what you've learned about the nature of that function in some other part of the data domain. So this basically becomes a linear combination, a linear superposition of basis functions where these C values are the parameters that you have to learn. And I'll come back to this later, but one of the nice things about this is you can start with a very low order B-spline, where you only have a very small number of basis functions and therefore small number of parameters. You can learn a coarse approximation to the function. And then after you've learned it, if you get more data, you can come back and starting from that coarse approximation, you can refine it and learn a much more fine-grained approximation to that same function, which has more detail and local variability, which seems very consistent with the way that we as human beings learn. You know, it's like you learn tennis, you kind of like first you just learn to get the ball over the net. And then as you process more and more information and play against better and better opponents, you learn to refine your reactions as you get more and more data. And so this lends itself to that in a very nice way. You'll notice that it's basically a linear combination of basis functions. So the important thing is the choice of these basis functions. And they choose to use B-splines, okay? Which obviously, if you had different kinds of functions, you might want to look into it, but B-splines are pretty general. You can learn very, very interesting and complex functions which have a second order differentiability everywhere. So they do this, and then using that, they end up with the prototype can that they're going to test in this paper. What's interesting about these, of course, is that they become more easily interpretable, as we'll see. Part of that is by the fact that the functions are all univariate functions. So you can plot them and you can look at them, right? That's important, part of the can theorem. Okay, some comments on training and performance. Here's some tricks they use in order to make this neural network, CAN-based network, more easily optimizable. So one very interesting thing, I think, is that what they do is they learn this function as a combination of B-splines plus a prior basis function, this bx, and this weight is just a weight to change the values, not actually necessary. And what they use as this prior basis function is the CLU activation, which is shown here, which looks rather like a rectified linear unit, except it's continuous. In other words, this CLU becomes the prior on your activation function. And then what they learn using the spline is the residual to this activation function. So they use a residual pathway approach to learn the form of the edge function. Okay, and I'll show a picture of what that'll look like in a minute. And what's interesting is that you could turn the spline off, and then basically you'd have something very similar to what we have in current multi-layer perceptrons, which is basically an on-off switch, right? And it's linear, so x is linear as long as it's larger than some value, and then it's set to 0 when it's smaller than some value, which is typically sort of consistent with a lot of physical modeling representations. And then they parameterize the spline as a linear combination of B-splines, as I said over there. This parameter W that they put there is in principle redundant, but they include it just for training because they find it helps with the training and to better control the magnitudes. And then to initialize these, I call them activation functions, but really these edge functions. They initialize each, the spline x to approximately 0.2 by drawing coefficients from a Gaussian distribution with sigma about 0.1. So this is just their ad hoc initialization for training mechanism. So 0.2, of course, is some arbitrary number there, which basically means you're taking CLU and adding a constant to it, and then you're learning how to modify that constant. Oh, and then W is Xavier initialized as you do in a normal multi-layer perceptron. And they can update the grid of these spline functions. So if, for example, the data only is in a particular realm and you need to extend it, you can extend the B-spline to have a larger extent. As I said, you can make it more fine-tuned and so on and so forth. And then they can use this concept of grid extension that I mentioned before to fine-tune it. So because B-splines can be made arbitrarily fine-grained, what you can do is you train it with a smaller number of basis functions in the beginning, so you've got fewer parameters. And then once you've learned a basic shape, you can then extend it by making these spline grids finer by putting more and more basis functions, which are more local, and therefore you can learn more local detail. I guess in principle, you could also use the residual training trick approach. They don't talk about it, where you could learn a coarse-grained function on top of the CLU, and then you could learn a fine-grained function on top of that. I mean, there's lots of other kinds of tricks that you could, in principle, play to learn this function. And so I'm going to skip all this, but this is basically just how they go about doing it. And here's a training example, performance example for this particular function, the exponent of the sine of pi x plus y squared, where they start training with a grid of 3, so 3 basis functions, and you can see that it saturates. And then they increase the grid to 5. They have a particular way of initializing this grid so you don't lose performance dramatically, but as you can see, you lose a little bit of performance. And then as you train the parameters again, it improves and saturates and improves and improves and improves. And the blue one is the training, the training performance, and the orange one is the test period performance. And you can see that around grid equal to 50, they remark on this thing, this vertical dash line is being called the interpolation threshold. And that's, they notice that the testing sort of falls off at about that level. And they associate this number, this grid equal to 50 as being associated with the number of parameters that they have to learn. Okay. So as they, I'm sorry, the number of data points that are being used to train this thing. So the number of parameters they have to learn, the number of grid points here becomes very similar to the number of parameters, sorry, data points that they have. And that's when the training stops. That's when they start overfitting to the data, and whereas the testing shows that that's about where you should stop. And they go all the way up to, 1,000 grid where things start to break down. Then they do the same thing, but because they know that this function over here is actually only needs a 211 can, not a 251 can, they train it, they pre-specify the architecture as being a 211 and train it. And you can see that because now they have fewer parameters, they're able to get to an interpolation threshold of about a grid, which is more fine-tuned at about 100. And you can see the performance is much better because they've used a lower order representation of that system with fewer parameters that they have to learn. So you get this sort of staircase drop behavior. The smaller can, which is lower description length, clearly generalizes better, and that's a nice thing. And then they go on to point out that in some sense, you can think of the cans as having two kinds of degrees of freedom, external and internal. So the computational graph, the overall structure, is sort of the external degrees of freedom. And then within each of the links, you have internal degrees of freedom where you can add or subtract more complexity. Okay. So the external degrees of freedom for learning the overall external compositional structure, and the internal degrees of freedom for learning the form of the univariate functions. And then they show this performance of test loss against grid size, and they have this g to the -4 scaling law, and they show that the cans, different cans, so here you've got the 251 in blue, the 251 in black and the 211 in blue, and you can see that the 211 initially has higher test loss, but then it passes the 251, which saturates, and it continues to come closer to this g to the -4 scaling law. So this is between 3 and 4. Okay. And then they look at the training time associated with that, and they say, in principle, the training time still remains more or less constant, regardless of the grid size. So it seems to scale favorably until you get to very, very large grid sizes compared to the number of parameters that you, data that you have. So very, very large parameters. Okay. I will make a comment that a gentleman from Stuttgart, who's at the conference, the meeting in Switzerland, ran this on some of his test problems, compared them to his approach. Is Manuel here? Manuel, it's something to do with chaos theory, right? Do you know what I'm talking about?
Sergey.
Sergey, yeah. Do you know
So-
what the work that he's doing?
So he would be maybe comparing against polynomial chaos.
That's right, polynomial chaos, right. So he ran this and he compared this to polynomial chaos, and he was quite favorable about the performance he was getting with the cans. I don't have anything to show, but he reported that when he was running it, testing it. So he was able to download their codes and put them on his machine, and in 3 or 4 hours he was running examples, which is very cool. Yeah. Another thing is this idea of local learning and continual learning as you get more and more data, and the fact that multi-layer perceptrons tend to suffer from this thing called catastrophic forgetting. And here's how they illustrate that. So let's say your function actually looks like this periodic sinusoidal or whatever function. And in phase one, they train it only from data on this part of the extent of x. And then phase two, they give it data from this part, and 3, 4, and 5. So they provide local data sequentially, just as an illustration. And they train a multi-layer perceptron of an appropriate size. Did they say anything about the size? No, I'd have to dig into the paper again. And so they train on the first one, and then they get this kind of behavior. And then they train on the second one, and you can see it forgets the form of the data around here, and then the third one, fourth one, fifth one. So you have this sort of performance that they report. I can't speak to it, but basically where they claim that with MLPs, because of the nature of the architecture and so on, because the parameters sometimes tend to have global effects on the overall performance rather than local, you can get this kind of forgetting behavior. Whereas when they train a CAN, so here's the function trained using only this portion of the data, and you can see the effect of the CLU, and then you put 2 and 3 and 4 and 5, and you can see that the updates happen locally, so that whatever you've learned already, you in principle don't forget, because of the structure of the way in which the univariate functions is learned. Some comments on interpretability. So the question is, how do we choose the CAN shape that best matches the structure of the data set? Usually you don't know the symbolic formula. If you knew it, you would know what kind of a CAN to use, right? So what they looked into is, how do we determine this shape automatically? And this is where they exploit the fact that the CAN theorem says you need 2D plus 1 nodes in the hidden layer for D inputs. So they start with a large enough CAN, something like 2D plus 1, and then they train it with sparsity regularization, and then they follow it with pruning, and I'll explain how they do that. And then they argue that these pruned CANs are much more interpretable because there's a strategy, a built-in strategy for pruning. And they make some proposals for simplification. Okay, so sparsification. So in addition to the regular loss function, they define this thing called the L1 norm of an activation function. So it's not an L1 norm over parameters, it's an L1 norm over activation functions. So they take all of its inputs, they calculate the activation function over those inputs, they average over the inputs, and they call that the magnitude, the L1 norm magnitude associated with that particular activation function. Okay, so for each of the links, they calculate the strength. And so now if you've got a layer which has n in inputs and n out outputs, you do this absolute value norm summation over all the activation, input activations and the output activations. So input, I'm calling them activations, but you know what I mean, the edge functions, okay, for each layer. And then they define this thing called the entropy of that phi, which is this on the bottom here, you've got the total sum. On the top here, you've got the individual ones. So you take the ratio, so you get something like a fraction or a probability, and they take that probability multiplied by the log of the probability, or that fraction multiplied by the log of that fraction, and then they negative this, and they use the analogy to entropy to define this a norm called the entropy norm. Okay. And then they compute the total training objective as being the normal loss function, your prediction loss function, plus this norm on each of the individual activation functions, okay, with a parameter mu1 as a weighting parameter, and then the norm over this entropy function with the parameter mu2, regularization parameter mu2, and then they add another lambda to increase or decrease the strength of the regularization. They usually set mu1 and mu2 to 1, so they use L1 norm plus this thing they're calling entropy, and they add that, and then they just vary the lambda over there and control the regularization. Obviously, a lot to look into there, but that's their strategy for training in order to maintain compactness of this architecture. And then when they want, so notice that this is called the strength of the activation function over here, the average magnitude. So what they then do is for visualization, they plot these things as a graph, and they take the strength of the activation function, and they pass it through this tan hyperbolic function. And then when they plot the curve, they set the transparency of that line to be tan hyperbolic of this thing, okay? And so what it does is if the activation function is strong, it shows it dark, and if the activation function is weak, it shows it like very, very dim. And then after they look at that, after this training with sparsification, they look at the visualization, they look at those dark lines and weak lines, and then they prune out the ones which have low activation strength. And the way they do that is they take the activation strength, is this maximum over the, okay, yeah, yeah, I'd have to look into the details of this. But they basically they compute this kind of a score, and then they compare that score to some threshold, which in this case they set to be 10 to the minus 1. And if it's lower than that, the threshold, they say, okay, we're going to prune it out. Of course, this is all fairly abstract and empirical, but this is the strategy they use in this paper. And then if they, and I'll show this, if for functions that they suspect to be replaceable by symbolic functions, like symbolic learning, they replace them like a cosine or a log or an exponent or something, then they've got a program which basically replaces those particular activation functions with symbolic functions like sines and cosines and so on with parameters. They optimize those to the parameter, to the function that they've learned, and then they put it back in the network and they retrain the network, but now using cosines and sines or logs or whatever in place of those functions. Okay, so here's the example. So let's say the actual function was exponent of sine pi x plus pi y squared. You start with this 2 inputs, 2D plus 1 hidden layer, 1 output node. And they train it with sparsification. And now you can see the strong activations are in dark black, and the weaker activations are in progressively shaded gray. And they look at this, and so you can see they're sort of ignoring these guys. They're focusing in on this pathway and this particular function that has been learned. Then this pathway, this particular function that's been learned, the summation of those two, this pathway. So ignoring these pathways, going down this pathway, this function is learned. And they basically say, okay, now we can prune the network down here without any significant loss in performance. And they replace that network with this network now, which is the simplified one where you only have one hidden node. So it's a 2-1-1 as opposed to a 2-5-1 can. And then they look at this and they go, this thing looks like a sine, so I'm going to replace it with a sine function using this fixed symbolic. And then they train it a little bit further. And then they say this thing looks like a squared function, so I'm going to replace it with a squared and train it a little bit further. And then they say this thing looks like an exponential function, I'm going to replace it with an exponential and train it a little bit further. And they also have a program where they say that if you're not quite sure what to use, they actually have a program which compares it to standard kinds of functions and suggests a possibility for you. And then you retrain it again after having done that, and you now learned this symbolic formula, which, and then they have this operation called snap, which basically takes numbers that are very close to integers and replaces them with integers, if you remember that from the previous paper, Techmark's paper. And this 3.14 parameter that's been learned is replaced with pi and so on. And that's essentially how they learn this interpretable function. Okay. They make some comments about why not symbolic regression. They say it's reasonable to use symbolic regression, but they are in general brittle and hard to debug, and they tend to either return success or failure without outputting interpretable intermediate results, which you could examine. So here's an example where they would use this thing like I know what that is, a Bessel function or something, to try to learn this function. Okay. In contrast, because the cans are doing continuous search in the function space, the results tend to be more continuous and more robust. You have more control, more transparency. You can do debugging and so on, and this sort of level of control. I don't know much about symbolic regression, but these are their claims. And then they go on to say when the target function is not symbolic, then symbolic regression will fail, but cans can still provide something meaningful. And you could at least get some ideas as to how you would want to replace those learned functions with algebraic or equations or whatever. Okay. So say, for example, a Bessel function especially would be impossible to learn using symbolic regression unless you provided it in advance. Some other comments. These are my comments now. They claim no linear weights and at the beginning of the paper, but I want to point out that having gone through it, you can see that that's not actually quite true. At least when they're using B-spline approach, the B-spline basis functions, it's really analogous to learning multi-layer perceptrons on each of the edges with the B-splines as activation functions. Right? So here I've taken this 251 can, and there's the equations of that. And if you substitute in the B-spline plus the CLU, the residual pathway plus the CLU, and you put that in, the psi functions look like that, the phi functions look like that, right? And basically you can just substitute these in these equations, and you can see basically, yes, you have a lot of effectively linear trainable parameters throughout your entire network. So what you're learning is really not that different from a multi-layer perceptron, except that it's been extremely strongly regularized in a particular way. Okay. So remember again, that's what the CLU looks like. If you take this function and you imagine it as a multi-layer perceptron, you can see that it looks like a bunch of B-splines which are fixed on a particular grid. One weights, output weights that you have to learn. This is your residual pathway. And then here's your CLU pathway. So you can initialize this to be some constant, and you can then learn to grow it. But you're always starting with this thing which looks very close to a rectified linear unit. Okay. Oops. Oh, I got animations here, which not intended there. And this is sort of how I visualized it. There's your basic CLU function, and then there's the function you're learning on the top of it, and you're adding these two together to get your nonlinear function. So instead of starting from scratch, you're starting from something that looks like a CLU. Okay. Some other comments. In principle, you could think of these activation functions on edges as somewhat similar to context-dependent gatings that we use in LSTMs, because that's what LSTMs are. Again, there are no weights on the connections. You've only got these gates, and these gates are basically functions, right, which are dependent on something or the other. And so in that sense, you could say it's also very similar to the learnable gates we use in the mass-conserving perceptron networks, which we've been developing for interpretable machine learning. Comments about strengths. So cans are I'm going to claim a strongly architecturally regularized form of machine learning perceptron. In principle, the theory says you need 2D plus 1 pathways if you've got D inputs. And they have this kind of hierarchical global local architectural form, right? The global form is given by the Kolmogorov Arnold network theorem and its extensions. And then the local architectural form is the learning of these local functional forms. Okay. But you're guaranteed, as long as you have enough flexibility, you're guaranteed by the Can theorem to be able to learn any multivariate input-output transformation. As I was thinking about this morning, you could think of these edge functions as not terribly different from the thing that we know is present in human brains or organic brains, which are these things called nerve bundles, where we got a bunch of neurons which work in concert to learn a particular kind of relationship. And then you put bundles of bundles together and so on, and you construct these more complex learning mechanisms. Edge functions use residual network strategy, starting with the CLU activation function as a prior. And I think that's very interesting because that means that in principle, you could actually pre-specify these edge functions using theory and then update them using Bayesian updating. In this case, they used a CLU as a prior, but let's say you're trying to represent evapotranspiration in a particular model, and you have an initial prior on what that should be, what you think it is, you could put that in as the prior. And this is not different from what people are doing now in physically informed neural networks. So you could do a kind of Bayesian updating. This thing is interesting that B-splines are pre-specified on a grid over some extent, and that you can go from coarse to fine. I think that's kind of cool. I pointed out that there's a strong relationship to the kernel trick used in surrogate vector machines, and I think that's worth exploring more deeply. And then there's this, because you're using these locally adjustable splines, you can do this kind of local global learning where you don't have catastrophic forgetting. So as you get new data in some part that has never seen before, you can learn to modify your activation functions without having to mess with the rest of the architecture. Then you can prune the network starting from some architectural prior, and in principle, they can be both interpretable and accurate based because of that. And I didn't get far enough to draw this figure, but this is what I was trying to illustrate. Whereas in a standard machine learning architecture, you would have a fully connected architecture. Typically, you've got these locally connected architectures where you're learning these local representations and then you're summing them together to combine. So there's a kind of a weight, you're saving parameters in some sense by doing that. Okay. Some potential improvements that I think could be investigated. I know, for example, Yang is very interested in generative modeling. I think it would be very, very cool to explore how this concept could be extended to probabilistic generative modeling. So you could learn a representation of uncertainty. Manuel is also interested in that. I think we could generalize the edge functions to increase their context dependence. So right now they only depend on the input coming in, but you could make it a conditional representation, conditioned on other things that are going on, much in the way that Yuan has done with his multi-layer, with his mass-conserving perceptrons, or what is done in transformer networks where you learn context dependence gating. And so just some throwaway, hand-waving, throw-out comments there. You could incorporate other important concepts like spatial convolution, kernel filters. You could have spatial filters where you learn the extent of the shape of these filters. Context-dependent conductivity gating, context-dependent or flexible attention, maybe weight sharing by sort of pre-specifying the basis functions is a form of weight sharing because you're You're basically saying, I've learned a bunch of functions and I'm going to reuse these functions over and over again. And then building compositional architectures where you progressively add depth in order to learn more complex representations. So that's my justification for why I'm convinced that CAN theory is going to be an important part of future ML and scientific investigation, based on just reading this paper. People have sent me some other papers. There's something called HippoCAN, and there are other ways probably of approximating these functions that could be explored. There's clearly issues to do with training, because they show some examples where very large networks, they have difficulty training using this approach or this concept. And so I think people would have to dig into that. So with that, I will throw it open for discussion.
Great presentation, Hoshin. Thank you so much. I have a like a quick question. I was wondering if you could comment on. So like many years ago, like 10 years ago, when I was doing my undergrad, I kind of was super interested in this sparsity features of machine learning algorithms. Specifically back then, like there was a trend for extreme learning machines and like Boltzmann machines for regression tasks. So my experience like back then was that generally they were used for feature extraction and feature importance. But as we kind of experimented on them, it was shown that the accuracy not necessarily increases by increasing the sparsity, and that considering the fact that the encoded space using whatever method we use, if either like in transformer or LSTM, is much larger based on its dimension compared to the experiments they did in their paper. Do you think the sparsity would be beneficial for mapping that context to the target?
So there's some interesting work on pruning being done. You know, you're probably familiar with the lottery ticket hypothesis paper, where they looked into pruning.
Yeah. Yep.
So there's some interesting thing there. My own feeling is that there's sort of a bit of a trade-off in principle between interpretability and accuracy. So if you look at the equations, the physics equations that have been learned or fit to data, there are other people who have used various kinds of symbolic regression learning strategies, and they show that when you give a person a data set, a real data set, as opposed to one which was generated from a synthetic example, there's no unique answer as to what the underlying physics of that equation is. You have to decide at some point when you're going to stop. And a lot of it has to do with how much data you have and so on and so forth. So, you know, this concept of description length becomes very important because it relates, as you have more data, you can in principle build a higher description length representation of the system. But there's no correct, unique representation other than the one that you and I or scientists in general have agreed on as being the electromagnetic wave equation or whatever it happens to be. And so what people end up doing is they end up choosing a particular representation. So just like you have the snapping, so you got a number and you learn the number, and when you fit it to the data, you get 1.035. And you go, oh, well, you know, that 0.35 is not important. I'm going to throw it away and just replace it with 1. Or it's 3.1426 or something. Well, that's close enough to pi. I'm going to replace it with pi. So I think in scientific investigation, we do a lot of that. And at some level, we sort of have to make this sort of decision between ease of interpretation versus accuracy. And in principle, when you're going to try to explain it to somebody else, you might abstract it and simplify it even more, right? So it all depends on the level at which we're working. I don't know if that makes sense to you or helps, but that's kind of my perspective on it, is that we probably want to use a description length perspective when doing pruning with the with the understanding that as we prune, we might sometimes be giving up accuracy in order to gain interpretability.
Yeah, thank you so much.
I'm wondering if did they show that their new CAN symbolic regression methods can outperform their previous AI Feynman?
Good question. Let's take a look. Where's the paper?
My other question was about the B-spline. So I guess they're just using regular B-splines, right? There's no smoothing penalty on the neighboring coefficients.
I didn't dig into it too deeply, but I believe just from the pictures, I'm interpreting that they're using regular B-splines, and there are different kinds of B-splines, uniform B-splines. There are various kinds of ways of doing B-splines. They don't actually get into it. So what was the second half of your question about regularization?
Yeah, are they regularizing the to kind of enforce smoothness on the neighboring coefficients of the B-splines?
They don't say anything about that. To the best of my knowledge, they are just using that L1 norm and entropy regularization. So I guess one could look into that and see whether that would have that effect or not. I do believe that somewhere in the paper they talk about comparing, let's see, AI Feynman data sets. Say for each data set in each model family, we plot the Pareto frontier and plane spanned by number of parameters in figure D1. We can go look at that. We conjecture that Feynman datasets are too simple to let CANs make further improvements in the sense that variable dependence is usually smooth or monotonic, in contrast to complexity of special functions, which often demonstrate oscillatory behavior. They also have this comment about automatically discovered CANs tend to be smaller than human constructed ones. Let's go look at that. Yeah, sorry, without digging in to it, it's hard for me to comment, but they do have a lot of stuff here that this paper is already so long that I wasn't able to get through all of it yet.
Yeah, no problem. Thanks.
Sure. But they do a lot of testing on different kinds of data sets. Oh, they even comment about, I didn't see this. They even comment about learnable activation functions. Comparing it with learnable activation functions. That's a natural question. They say learnable activation functions are conceptually simpler than CANs. They scale better than CANs. But the cons are they seem to be less interpretable, and they also seem to be less accurate, but still more accurate than multi-layer perceptrons. And then they do some interpretability. So yeah, I'm going to have to dig into this. And there's just a huge amount in this paper. Here's their figure about should I use CANs or MLPs, where they've got accuracy, interpretability, and efficiency, and various kind of conditions they suggest. So if efficiency, fast training, you go to MLPs. If you want this either fine. So the only one which says MLP is this pathway over here. So obviously their bias is towards cans, but there's a lot of places where they say either is fine also.
Hoshin, do you believe that using B-splines are kind of the best way because are very flexible so that they can be used for nonlinear functions, or are there any other alternatives that might look better?
So from my digging in, I see on the internet, if you Google on YouTube B-splines, there's some very nice videos. There's one by Freya, something or the other, who's a game designer. And B-splines apparently are very actively used in building game worlds because of the nice properties, the local properties and the second order differentiabilities. Because when you do objects moving, you don't want you don't want acceleration to change abruptly, right? Like, you may have had that experience when you driving a car on a banked highway. If the curvature changes abruptly, you get a jolt, right?
Mhm.
Yeah.
Right.
So apparently it's very popular in game theory because of its local properties and its flexibility and so on. But I could imagine that there would be situations in which you might want discontinuities or some other property, and
Mhm.
then in that case you would have to modify or use some other slightly modified approach to do that. Here they're focusing on smoothness and continuity as a requirement. But
Mhm. Yeah, I was thinking on that because usually data is not as smooth as we want it to be. So I was considering like, oh, maybe a function that can deal with that. Or
sure.
yeah.
Sure.
Okay,
I mean,
thank you.
I've seen people do change detection where they
Mm.
use nonlinear regression, but then they put in a threshold function which allows you to detect the point of change, and that would be a
Mhm.
discontinuity. So in principle, I guess that could be part of um, part of a learning system. Yeah.
Oh, Shin, I think I read it in the paper that they say that the training takes 10 times more than NLP. Can you comment on that? I think it takes more than usual for the MLPs. Let me see if I found where I read it.
Um,
And I think that it was kind of the only downside that I see on this. Like taking longer for training.
where did you see that? Which page?
I need to find out. Yeah,
Okay.
I don't remember. I was partially asleep maybe. Uh,
There is some comparison here for a PD example. Um, in this case, the green is the multi-layer perceptron, the blue is the CAN.
mm. Or maybe it wasn't here. Maybe I read it somewhere else.
Yeah. Oh,
Okay.
here. Currently, the biggest bottleneck of CAN lies in its slow training.
Yes. Mm-hmm. There.
CANs are usually 10 times slower than MLPs given the same number of parameters. But they
Mm-hmm.
do point out that the CANs have less parameters.
Mm-hmm.
So there's a trade-off there. We should be honest that we did not try hard to optimize CAN efficiency. We deem the slow training to be more an engineering problem to be improved rather than a fundamental limitation.
Mhm.
One wants to train fast, use MLPs, but if you want if you care about interpretability accuracy, slow training is not a problem. Yeah, I think that trade-off with number of parameters is an interesting issue. And also, I like the idea that you can train with less parameters with coarse grid representations, and then refine it and add more parameters, and then continue training. And I think they did a little bit of that here, but they don't talk about it very much.
Mhm. Thanks, Sochi.
I think the important takeaway here is actually, I mean, the part that really I find very interesting is the fact that you can take a multivariate function and compositionally reduce it to a set of univariate functions, which are then combined together using just addition. And I think that is worth thinking about because um, presumably it has some interesting information theoretic implications that might be worth digging into. But it does make it an interesting way to think about compositional multivariate functions, um, uh, which lends itself towards this idea of being better able to understand what they're actually doing and how they interact, the different components interact with each other. And then the fact that the theory kind of gives you some
Sure thing.
Siri trying to talk to me, that it sort of gives you some idea as to the size of the network. So it gives you a prior to work from, which I think is also very interesting. Okay, here's the thing about accuracy and number of parameters. CANs can achieve better accuracy than MLPs with fewer parameters in the signature classification problem. Soon after our preprint was first released, Professor Lab from Georgia Tech discovered an MLP with only 60 parameters is sufficient to achieve 80% accuracy. Anyway, like I said, it takes a long time to actually absorb everything in this paper. Okay, any other thoughts or comments? If anybody has any familiarity with support vector machines and the kernel trick, the idea of projecting from nonlinear to linear spaces, and has good insight into that, I'm very interested in talking to them about it because one of the things I'm really trying to understand is, you could start and you could understand machine learning and information theory purely from linear perspectives. And so you just have, all you need is linear algebra, linear vector spaces. But then when I dig into it, I see that mathematicians make comments that you can extend this idea of vector spaces to nonlinear spaces. So for example, you can imagine a vector in a linear space where the space then becomes curved, and so the vector then represents this function, which is linear in the curves in the actual space, but appears nonlinear in our transformed space. And so since the basic operation that multilayer perceptrons are largely doing is similarity dot product computations followed by switches, I start to think that you can interpret nonlinearity as being something like adding a kernel trick on top of similarity dot products and switches, you know, as a kind of like a primitive way of understanding what's actually going on. And so I'm really interested in learning more about this kernel trick, if anybody has any understanding of it or insight into how that comes about and its relationship to projecting from lower dimensions to higher dimensions and back. I believe in groundwater there is a particular kind of projection which allows you to project your groundwater system into a space where you can do linear transformations, operations and back, and I've forgotten the name of it. But I know people in groundwater are familiar with this trick. So it's a trick that's very commonly used, not unlike when we take Laplace transforms and we convert integration to multiplication, or logarithms where we convert multiplication to addition.
Talking about overlapping wells,
Uh,
or
is somebody's name associated with it, but I can't remember now. I think it starts with K also. It's a particular transform they use in groundwater to make things more linear, and then they solve in that transform space. I'll try to look it up. Yeah. Something projection or something. I can't remember.
they're solving the whole flow field is what they're solving.
I think so. Again, I'm not a groundwater person, but yeah. But I mean, it's a common trick where when something is difficult to solve, you project into another space, right?
Right, yeah.
And so it feels like this is what they're doing over here. They're taking nonlinear functions and they're using the sort of kernel trick to project it in a way that now linear operations, you know, it's like how you do classification of things that are not easily classified using linear decision boundaries. You project them into another space using the kernel trick, and then you can use linear decision boundaries.
I did study that like 6 years ago, but it didn't really stick with me. The kernel trick. I should go
Okay.
back to it.
Sure. Luis?
Coaching. Given that here we are comparing just CAN versus MLP, do you have an idea how we can add memory here? Kind of a more direct comparison with LSTM, this kind of structures?
Yeah, in principle, I don't see why not, because what is recurrence other than adding an input, which is the past value, right? So at the recurrent node, you could still reinterpret it as a CAN, right? As a mini CAN in principle. And all you're doing is saying that I need the value from the last time step as another input. So in principle, I don't see any, it starts to become more like a deep network, right? Just like an LSTM or an RNN is a deep network. And then as I mentioned, there's this concept of activation functions on links is not dissimilar from gating functions. So you've got input gates, output gates, and remember gates or forget gates. And they look very similar to these functions, except that they're not necessarily univariate. So those functions could be compositional using CANs. That's assuming you needed the complexity that a CAN can give you, right? If you can get away with a simple sigmoid function, then why not, right? Yeah. But in physics-informed neural networks, very often you have these process equations, and you've got priors, which scientists have learned in the past. And if I'm not mistaken, they very commonly add a neural network as a residual network to those equations to learn modifications to them. And this sounds like a kind of trick that is very similar to what they're doing over here, where they're starting with a CLU and then adding B-spline basis functions on top. Back when Natalia was working with me and we did the Bayesian estimation of structure work, we did something similar where we basically said you could try to guess the conductivity function first, and you could put it in as a prior, and then you could correct or update it. So I like this idea of being able to do Bayesian updating.
Any other questions?
Comments, thoughts? I'm certainly not the expert on this. I'm just telling you what I've learned, but hopefully this stimulates some thoughts and investigation. And I'm particularly interested in the sort of the information theory perspective on trying to understand all of this stuff.
Thank you, Hoshin, for putting this together and for all the examples and all the insights. I think, yeah, digesting a 50 pages paper about a new concept is really cool what you do. Thank you so much.
Yeah, thank you very much.
Yeah, and with that, I just have a few announcements. So thanks to Manuel for putting together this list for AGU 2024. So for those attending in person or online, you can find all the contributions of the team in AGU. Yeah, I hope you all have a fun time in December in AGU. And this is actually our last session for this year. So we are gonna see each other back in January. So Christina is gonna be presenting, and we also are gonna have some presentations scheduled by Julie, by Isabella, and Hoshin also might present next year's, but I'm also gonna share our calendar for the next session in case you want to present your research or practice your presentation. So please add your name to the list. And if you have any interesting papers that we want to read together, in the spreadsheet in the second sheet, you will find the wish list, which are some added papers. You can also add your papers if you think something is interesting. Yeah, and with that, thank you so much, everyone, and yeah, enjoy AGU, and we'll see you each other next year.
Before we go, I just want to mention, I know that Luis did some very interesting work that he's getting his paper out soon, so maybe we can get you to talk about that, Luis, in the new year, the SWE paper. And Yang is working on this generative modeling paper, and also the adversarial testing stuff. And I know he gave the talk at CMWR, but I think it'd be very cool for him to present that stuff to this group because there's some very, very cool stuff coming out of that. So I just want to mention to people that, it doesn't have to be reading somebody else's paper. I know a lot of people are doing some very cool work, and if they just want to present it and get comments and discussion, this is a perfect venue for it. Yeah. And Manuel later on is variational LSTMs. All right. Okay, guys. When are we coming back together in January?
I have Christina for January 22, the
22.
22nd.
Perfect.
Uh-huh.
Okay.
Yes,
All right. So 2 months from now. Yeah.
exactly. Yes.
Everybody have a great Christmas and
Thank you, everyone.
talk to you all soon.
Bye-bye.
Bye.